Methanol bunkering, technical and operational overview. Key concepts. Decarbonization driver. The maritime industry is increasingly adopting low-flashpoint fuels, such as methanol, to meet stricter gaseous air emission legislation and reduce greenhouse gas (GHG) emissions from ships. Methanol's role. Methanol, CH3OH, can be produced from renewable sources, bio-methanol and e-methanol. Its adoption is expected to become a key strategy for the industry to comply with environmental challenges. Purpose of bunkering guidance. This material summarizes the technical and operational guidance necessary for safe methanol bunkering operations, covering challenges for both the delivering ship/landside source and the receiving ship. Methanol transfer system. Loading arms and supporting structures. Methanol articulated rigid piping, hoses, swivels, valves, couplings, emergency release coupling, ERC. Insulating flanges, quick connect couplings, handling system and its control system, communication system, emergency shutdown, ESD, ship/shore link used to connect the supplying and receiving ESD systems. It can also include the pumps, compressors, or blowers intended for the Vapour Management system. Methanol properties and onboard storage. Key properties. Chemical form. Clear, odorless liquid, CH3OH. It is water-soluble and biodegradable. Flammability. Methanol is highly flammable with a low flash point of approximately 12 degrees Celsius. The flammable range in dry air is wide, at approximately 6 to 36.5%. Flame characteristics. Methanol burns with a flame that is nearly invisible in daylight and produces no smoke. Energy density. Its energy density, 15.7 megajoules per liter, is significantly lower than conventional fuel oils, meaning approximately 2 to 2.5 times more storage volume is needed for the same energy content. Clean burning. It has cleaner burning properties, enabling reduced exhaust emissions like sulfur oxides, SOx, and particulate matter, PM, and emits less nitrogen oxides, NOx, than conventional fuels. Toxicity. Methyl alcohol is classified as toxic by the IMO's International Code for the Construction and Equipment of Ships Carrying Dangerous Chemicals in Bulk, IBC code. Storage requirements. Methanol is liquid at atmospheric pressure, allowing it to be stored similarly to conventional fuels. Cofferdams are generally required around methanol fuel tanks. Inoting is mandatory. The tank vapor space is to be inert at all times, ensuring the oxygen content does not exceed 8% by volume. Tanks must be equipped with a controlled tank venting system with pressure/vacuum, P/V, valves connected to a vent mast. Key properties of methanol are displayed for ready reference. Methanol fuel tanks. A main advantage for methanol as fuel is that it is liquid at atmospheric temperatures and pressures and thus can be stored in conventional tanks on board. Generally stored in integral tanks, although independent and portable tanks may also be acceptable. Methanol fuel tanks should not be located in accommodation spaces or machinery spaces of Category A. Furthermore, cofferdams are required around methanol fuel tanks, except because methanol mixes readily and is biodegradable in water. Methanol tanks can be stored next to the shell plating below the lowest possible waterline. Cofferdams are also not required where methanol fuel tanks are bounded by other methanol fuel tanks or the fuel preparation space, fuel pump room. The cofferdams, where provided, are to have gas and leak detection and be arranged for inerting or filling with water. The methanol tanks are also to have a controlled tank venting system with pressure vacuum, P/V, valves connected to a vent mast, and the vapor space is to be inert at all times such that the oxygen content does not exceed 8% by volume in any part of the tank. For fuel tanks and cofferdams, access is to be arranged from the open deck if possible. Regulatory and safety frameworks. Methanol, as a low-flashpoint fuel, is primarily regulated under the International Maritime Organization framework via the IGF Code of Safety for ships using gases or other low-flashpoint fuels. The international ship safety requirements are mainly based on the MSC.1/Circular.1621 Interim Guidelines for the Safety of Ships Using Methyl/Ethyl Alcohol as Fuel, adopted November 2020. The IBC code provides the initial basis for many safety requirements related to carrying methanol in bulk. Environmental compliance. MARPOL Annex 6 details regulations for the prevention of air pollution. The fuel supplier must document the fuel quality, sulfur content, in the Bunker Delivery Note, BDN. The supplier should also document the carbon factor, CF, especially if the methanol is derived from non-fossil sources. Classification societies/RO review design and construction against requirements. Flag administrations enforce international and national regulations for ships under their registry. Main bunkering methods. 1. Truck-to-ship bunkering, most commonly used method currently. 2. Ship-to-ship or barge-to-ship bunkering. Fuel is provided from a bunker supply ship to the receiving ship. Advantages: high flexibility, high bunkering rates, and high volume. 3. Terminal-to-ship bunkering, using a fixed pipe or hose connection from a land storage tank. Advantages: bunkering directly at berth, high tank capacity, fast bunkering. Bunkering interface and compatibility. A pre-bunkering verification is critical to confirm compatibility between the supplier and receiver. Equipment. Hoses and connections must be certified for methanol use and inspected periodically. Electrical safety. Earthing, bonding wire of the truck/ISO tank and ship is necessary to protect against static electricity, which is an ignition source. Emergency shutdown. ESD. Both the supplier and receiver must have compatible controls and monitoring, and both must be able to initiate an ESD of the complete transfer operation. A Vapour Management. Vapor return arrangements must be confirmed, especially as many ports are expected to require vapor return systems due to methanol's toxicity classification. Hazards and mitigation during bunkering. 1. Explosion and fire risk. Methanol liquid and vapor are highly flammable and easily ignited. Its vapors are heavier than air, relative vapor density 1.11, and can accumulate in low-lying areas. 2. Toxicity risk. Methanol is toxic. Exposure occurs via inhalation, ingestion, or skin absorption. Ingestion can lead to severe health issues, including vision loss or death, as it oxidizes in the body to produce formic acid and formaldehyde. Allowable occupational exposure limits are low as 200 ppm TWA. TWA is a time-weighted average, which is an occupational exposure limit that represents the maximum concentration workers can be exposed to over an 8-hour workday without risking adverse health effects. 3. Corrosion risk. Methanol is corrosive to certain materials, requiring methanol-compliant equipment for bunkering. Key mitigation measures. Fire detection. Since the flame is nearly invisible in daylight, fire detection systems must be suitable for methanol fires, typically combining smoke detectors with detectors that can effectively detect methanol fires, e.g., approved infrared, IR, flame detectors. Thermal cameras are also used. Firefighting. Use of alcohol-resistant foam extinguishing systems is required for tanks and bunker stations. Water spray systems are recommended over water mist systems. Handling. Closed loading, delivery, and handling systems are necessary. Toxicity control. Use of methanol gas detection equipment and proper personal protective equipment, PPE, is essential. Operational procedures and final safety steps. Before starting, the supplier and receiver must agree on the transfer procedure, ensuring compatibility between their respective manuals and systems. Key operational documents include the Methanol Fuel Transfer Systems Operation Manual and Emergency Manuals. Operational roles and training. A person in charge, PIC, must be appointed by both the supplier and the receiving ship to manage the operations, communication, and emergency response. All personnel involved require formal training, which covers basic methanol handling, technical safety, operational risks, firefighting, and emergency management. Risk assessment and safety zones. Risk assessments are mandatory to evaluate hazards and establish mitigation measures prior to operation. A simultaneous operations (SIMOPS) study must be conducted if other activities, like cargo or passenger loading, occur during bunkering, as they may introduce hazards, sparks, spills. Safety zones are designated ignition-free areas established around the operation where entry is limited to authorized, essential, and trained personnel. Verification. The role of checklists. The safe execution of bunkering relies heavily on checklists to confirm that all necessary steps are completed correctly. Pre-bunkering verification includes checking communication links, including SSL, fire detection and extinguishing equipment readiness, inspecting hoses/couplings, and ensuring remote-controlled valves are operational. A simplified sequence of activities of bunkering operation is displayed for ready reference. Thank you for watching the video. For more marine topics, please subscribe the channel. Please help us with your valuable feedback to improve the contents.